So now we're going to look at how acetic acid acts as a buffer. First, we'll come up with a definition of a buffer. A buffer is a solution that contains both an acid and its conjugate base. This is a weak acid and its conjugate base in solution. And if the weak acid and the conjugate base are both in solution in roughly equal concentrations, then it resists the change in pH when you add acid or base to it. And that means that it has a buffering effect. That's our buffer definition. And we're going to use this for a calculation. We're using the same concentration of acetic acid that we had before, but this time we've got 0.5 molar of acetic acid and 0.5 molar of the conjugate base, sodium acetate. We want to find out what is the pH of the solution. And this is an example that's straight from the textbook, zoomed out, so you can go back and have a look at it. It's also in my notes. But you can use the example that they've got in here and follow it through. What I'm going to do is actually follow it through using our ICE that we used previously. So if we look through this and set up our equation, we have two things. We have, again, our acetic acid equation, chemical equation, which has hydronium, or H+, and the acetate. But this time we know the concentration of the acetate. So we're going to start off with the initial, the change, and the equilibrium. Initially we had a 0.5 molar solution here, we had 0 here, and we had 0.5 molar here. So this would happen basically if you had two solutions and you mix them together. And ideally you'd have two 1 molar solutions, and when you mixed equal quantities of it, you're then actually diluting both of those solutions, so you have 0.5 molar of each. And what's the change? Well, let's have a look. It's minus X, so it dissociates a little bit, and because of that we're going to get a little bit of additional stuff here and a little bit more here. But that means at equilibrium we're going to have 0.5 minus X here, X amount of hydrogen, or H+, and we're going to have 0.5 plus X of the acetate, so we're going to have a little bit more. So our equilibrium constant is going to, again, be H+, and acetate ion, Ca minus, over the reactant, which is CH3COOH, acetic acid. And that, in this case, is going to be substituting in those things. H+ was X times 0.5 plus X. Put that in brackets, so you know you're going to multiply the whole thing. And then divided by 0.5 minus X. So you can look at that and go, oh, okay, well, I can multiply this out, or I can do the nice thing where I assume that if X is much, much less than 0.5, then I can make that really neat assumption by saying, okay, that means that this is approximately X times 0.5 plus a really small bit divided by 0.5 minus a really small bit. So it's really the same as X over 0.5 times 0.5. And these will cancel out, so it's roughly X, which is kind of neat. You sort of sit there and go, okay, well, that works. And remembering that our Ka here was 1.8 times 10 to the minus 5, so that's basically saying that is X. That means that that is our H+ concentration, so our pH of the solution is really the same as our pKa in this case, or approximately, which means that it's minus log of 1.8 by 10 to the minus 5, oops, which is 4.74. That's the pH of our solution. Now, a little check, is this 1.8 by 10 to the minus 5, is that much, much smaller than 0.5? Yeah, it's about a factor of what? 1,000 smaller, so it's much less than that 5% rule. Now, what happens if we add something to this? So the next part of this example was if you calculate the pH that occurs when 0.01 moles of solid sodium hydroxide is added to 1 litre of the buffered solution that we used here. So first off, I'm going to actually calculate the pH of how much 0.1 mole of solid sodium hydroxide would be when it was added to 1 litre of water. And this is a fairly simple calculation, but we'll run through it anyway. So what we've got is 0.01 moles of a solid in 1 litre. So it's basically 0.01 that's moles, molar solution. I'm going to put that in scientific notation, so 10 to the minus 2. And that is of NaOH. That's our concentration. But we actually want to find out what would the pH of the solution. This is what the second part of the question asks. What is the pH of the solution? Well, we can look at it and go, okay, well, this is hydroxide, so it's not going to be pH 2, it's going to be closer to pH 12. How do we work that out? Well, we know that our Kw, this is for dissociation of water, has to be equal to the acid times the base. So 10 to the minus 14 has to be equal to 10 to the minus x times 10 to the minus 2. And we want the x is basically this hydrogen. We want to find out what the H plus is. So minus 14 is equal to what minus 2? X is going to be 12. That basically means that the pH would be 12, but we can do it in a slightly different way by just saying, okay, if our hydroxide concentration is 10 to the minus 2, then our H plus concentration has to be 10 to the minus 12 to make it up to 10 to the minus 14, which means that the pH is going to be minus log of 10 to the minus 12, so it's going to be 12, which we know is a basic pH. Now, pH of water is what? 7. So by adding 0.01 moles of solid sodium hydroxide to 1 litre of water, we have changed the pH from 7 to 12, which is quite a large pH change. Now, let's figure out what would happen if we did this with a buffer instead. So, okay, so let's work on what happens if you added this sodium hydroxide to 1 litre of the buffer instead of just to 1 litre of water. Let's see, we have acetic acid, and if we add some hydroxide to it, we're adding hydroxide ions. So what's going to happen? Well, you're going to get some acetate and you're going to get water. What is going to happen before the reaction? So before the reaction occurs, we have 0.5 of this and we have 0.01 moles of that. What happens afterwards? We still have 0.5 of this, remember, because this is before where we had the buffer, which had 0.5 of each of those. After the reaction, and remember this is a strong base, so it's going to go to a complete reaction, we're going to have 0.5 minus 0.01. So we're going to have 0.49. This is going to go to completion, so all your hydroxide is going to be used up, and we're going to have 0.5 here plus 0.01, so 0.51 molar. So this is the molarity that we're going to use for each of these. So now we can set it up in the ICE. So let's set it up with ICE. Initial, change, and equilibrium. But our equation is actually different now because we don't have any more base. So we go back to the original equation where we have acid and acetate. But our acid and acetate concentrations are different because they're now, the initial is the same as this. So we've got 0.49 and we've got 0.51. And we have 0 of the H plus ion. So in our change, we're going to have Le Chatelier's principle is going to say, well, we have this thing, we used up all the hydroxide, and now we have to kind of fix that equilibrium. So we're going to try and lose some of that to adjust the parameters here. Let's see what we do. First, we lose a little bit here, which means we gain a little bit here, plus, and we gain a little bit here as well, so plus x, which means at equilibrium we're going to have 0.49 minus x, x here, and 0.51 plus x. What does our equilibrium constant look like? Well, let's see. Ka is equal to, again, our H plus and our acetate all over our acetic acid, which is going to be x times 0.51 plus x all over 0.49 minus x. And again, we make that assumption that x is much, much smaller than 0.51 or even 0.49. So the smallest one is 0.49. If we make that assumption, then we can look at this and say, okay, this is 1.8 times 10 to the minus 5. That was our equilibrium constant. And this is equal to x times 0.51, approximately, over 0.49. So it's actually slightly different to what it was before. So if we work this out, that means x is going to be 0.49 over 0.51 times 1.8 times 10 to the minus 5, which is 1.7 by 10 to the minus 5. And this is our H plus concentration. So our pH is going to be negative log of that value, 1.7 times 10 to the minus 5, which means it's going to be 4.76. Now, if you remember from our previous calculation, previously, when we hadn't added any of the hydroxide, we had a pH of 4.74. So this addition of hydroxide has changed the pH only 0.02. So the change in pH is 4.76 minus 4.74, which is 0.02. And we compare that to the change in pH here, where it was 12 minus 7, so 5, for the same amount in water. So this is an example of buffering. You can see that by adding a small amount of hydroxide, the buffer counteracts that addition and gives you a way of buffering the solution.